Well, that's some eye candy right there. We've all seen these inexpensive breakout boards on eBay and stuff. They're not bad. I mean, I've actually used them. They're pretty rock solid. Um, there's, I'm planning on making like a second number 2 video on e-stop wiring. And I thought, hey, I'll use the printer port as an example this time instead of Mesa. So I grabbed one of these bobs and plugged it into the computer. Printer port. Yeah, and zip drive cables work really well for this, just so you know. But one big issue with these bobs is that they don't have any kind of charge pump. So what you get, like the computer's off right now, but what you get when you turn on the computer and this breakout board gets powered, it's going to output anything that's on the printer port until LinuxCNC is launched and actually sets the output to what you want it to be. So these breakout boards don't have any kind of like watchdog or charge pump circuit. So you'll see as I launch the computer, you see the relay comes on, which now if you had that, say, running a spindle and you powered up the machine and then powered up the computer, the spindle might be on depending on how it's wired. Stuff like that. So you want to have a system that when they're shut off, and now Linux or the OS is launched. So what you ideally want is some way to not power the outputs until LinuxCNC starts, which usually involves a watchdog or some sort of charge pump circuit. So that's what we're going to do. You can see there's this pair of wire coming out of here. I actually soldered it to, I think it's pin 16 of the printer port, because that's what I'm going to use to activate the charge pump when LinuxCNC starts. It's kind of like a proof of concept type thing. I'm probably just going to wire it through a relay to the power coming into this breakout board for now. So let's get started. So Maris of Gecko Drive fame drew up a couple of charge pump circuits, and this one is the simplest. It has 2 diodes, a megohm resistor, 0.001 microfarad capacitor, and a MOSFET. This one's quite elegant. It uses the gate capacitance as what the charge pump is charging, which is kind of cool. And the reason why I built this one is because this is what I had in my basement for parts. I actually pulled the MOSFET off of a video card to play around with this just to see if it would work. So you can find this circuit online if you just do a search for charge pumps, and probably Maris. So this is what we have here. So, and honestly, all the parts aren't exactly the right size because it's what I had here in the basement. Like, it isn't a 1 megohm resistor, it's probably like a 500 k ohm, and they're not Schottky diodes, they're just regular diodes. It's just what I had, but it seems to work, or seems to work the way that we need it to act as a charge pump. So, alright, so here is the charge pump circuit I made, and I'll start this back up again. I'm just running Linux, one of the printer port stepper inch sample configs from LinuxCNC. And what I'm going to do, so here's the charge pump, here's the 24 volt circuit, here's the relay that I'm using to have the charge pump turn on. You can see that the breakout board doesn't have any power running to it, and there's where I tapped into pin 16, I think it is. So I can run the charge pump directly from the printer port to activate the relay to turn on the power to the stuff I want to turn on to. Now this isn't really super safe because there's no e-stop in this yet, but we'll get there. This is kind of explain how the charge pump works and how I'm going to set it up in LinuxCNC. So, as I've done in other videos, I like to use the HAL command interactive command line to play with this kind of stuff. So what I'm going to do is start the command line, and so I need a signal to activate the charge pump. The Maris's circuit calls for 12.5 kilohertz. Well, I think that's a Mach thing. Like, I don't know, maybe that's what it outputs for a charge pump. But we can kind of play around with it with LinuxCNC. I am going to, well, you can see here I'm going to use PWM-Gen. That's a software pulse width modulation module within LinuxCNC. So what I'm going to do is I'm going to load that, and reading the man page for it, it is PWM-Gen and then output, oops, spell it right, output underscore type equals 0. So there are different output types for PWM-Gen. I only need a single output. I don't need pulse width modulation plus direction or up down. So I'm using type 0. So if I hit enter, it loaded. Now there are two functions that make up the pulse width modulation generator within LinuxCNC. There's the make pulses, which runs in a base thread, and then there's update, which runs in a servo thread. So I'm going to add those functions to the two threads. So if I go add f PWM make pulses to base thread, and f PWM-Gen update to the servo thread. Alright, so now if I look at the pins, there are all the pins that make up the PWM-Gen. So I want a 50% duty cycle signal, so I'm going to set value, oops, 0, if I can spell right, 2.5. And I am going to set the frequency. I'm going to kind of show you what this charge pump is going to do I'm going to set the frequency to 100 hertz right now. PWM, let's, I'm going to set it to 100 hertz. Alright, so the scope is the yellow, is that yellow? Yellow traces looking directly at the printer port pin. So if I enable, let's see if this works, if I enable the PWM gen, I don't get anything. Let's look at the pins. So the value is 0.5, the frequency is hold on. That's set to auto. Okay. In which channel one? Okay. So what did I do wrong here? Oh, I never hooked the pin up to the pulse width modulation generator. So I'm going to net PWM sig. So I'll show you this. PWM to pair. Tab completes your friend. 16. So what this is doing is this is saying net, which is kind of like hook these things together using this signal that I just created, I just made up. So think of this as the wire. So I'm going to take the PWM sig wire and connect the pulse width modulation output to the parallel port pin number 16. So if I hit enter, you can see now, let me change we have a square wave on pin 16. And the frequency is 100 hertz according to the Rigel. Alright, so, and you can see the voltage across the coil is 0.3 volts. So let's increase the frequency to 1000. And now you can see the frequency is increased. It's 1 kilohertz and it's 3 volts across the coil, which isn't enough to trip it. So let's see what 2000 does. I can actually hear it. I can hear the coil modulate, humming at 200 or 2 kilohertz. So there we got 11 volts. We're getting close to tripping it. It isn't tripped yet. So let's try 3000 hertz. Okay, I just heard it click. So, and then you can see it's 22 volts across the coil. So a minimum of 3 kilohertz with the circuit components that I have here to trip the relay. But I want to do 10 kilohertz. And there's 10 kilohertz, and we get almost 24 volts across it. So if we then disable you can hear the relay turn off, and now if I enable it again, alright, so there's the charge pump circuit turning the relay on when a signal is sent to the charge pump circuit. So so that's setting this up so that it will enable the relay when a 10 kilohertz signal gets sent to the charge pump. So now we can use this relay to power the breakout board. So I'm going to probably use the same power supply, which is got 24 and 5 volts, to power the breakout board when the charge pump is enabled. So stay tuned. I'm going to do a little wiring, and I'll be back. Alright, I'm back again. So I wired, as you can see by the mess here, I wired in the relay so it turns the power onto the breakout board when the charge pump is activated. But in the process, I had rebooted the computer, and I didn't put any of the configuration that I did into the HAL file. So you get to see me do it again, and I'm going to do it a little different because I want to do 2 PWM gens, because I want one for the charge pump, and I want one for the analog out, because we're going to do that too, just to play around with it, kind of show you kind of what goes into it and what it does. So let's see if we can make this work. And I'm also going to hook the charge pump into the e-stop signal, so when I pull the e-stop out, the charge pump activates. So let's see if we can make this work. I'm going to go into the HAL command, and I'm going to load RT PWM gen output type 0, and then I'm going to do output type equals 0. So this should load 2 PWM gens with just a single output, and it didn't. Alright, hold on. Let me see how it's supposed to be. Oh! I was too verbose. So that's all you need. Okay, so now if we look at the pins, we have 2 PWM gens, 0 and 1. So we have to add the functions. The make pulses goes to a base thread, and the update goes into the servo thread. Alright, and remember we need to net I'm going to call it different, to PWM 0, PWM to the parallel port pin, what was it, 16? Out. Alright, so let's look at the pins for 0. So we're going to set PWM gen the value to 50% or 0.5. Oops. Just bear with me here. Scale 0.5 and PWM frequency to 10,000. And then let's look at what SIGs we have for e-stop. SIG. Okay, so we have an e-stop loop. So what I'm going to do is I'm going to hook the e-stop loop to the enable of the PWM gen for the charge pump. So all we have to do is we have a signal called e-stop loop. I'm going to say net e-stop loop PWM 0 enable. Alright, so if I look at if I do this, I'll clear that error that I did. And that didn't work. Hold on. Let me look at the pins. Oops. Make sure I'm on the right window. Alright, so we have enable is hooked to the e-stop. Charge pump is hooked to the PWM. Scale is, I did the wrong one. So scale needs to be 1. That's just setting the scale of the component. What we want to do is the value is 0.5 for 50% duty cycle. Now, if we turn this on, we get a PWM signal on the charge pump and the relay pulled in. And if you look, it's lit up now. So we got both 24 volts and 5 volts going to the breakout board. So if I turn it off, you see the LEDs go up. So we're going to turn this back on again. And we have the charge pump now supplying the supply voltage to the breakout board. Only when we have LinuxCNC and the out of e-stop. So this isn't perfectly safe, of course. It's still using LinuxCNC as the e-stop loop, which is software and I don't like it. But we could make an external e-stop loop that also uses this relay as part of the logic, so that if this relay drops out, the e-stop loop gets activated. It would be just one more in the loop of safety for this machine. So, alright, so if we look, now let's play around with the analog output, since how we have 24 volts hooked in, which is what is needed for the analog out. So if you see right now, it is it is 10 volts, and it's actually reversed because I have these reversed. Let's make it so that the OCD people are okay with this. There. So we have 10 volts right off the bat, which is obviously wrong. But if we disabled this, you'd see it would go to 0 because there would be no voltage anymore. So I'm going to enable this. I'm going to play with the second PWM gen that I created. I'm going to look at those pins. Set show pin PWM. Let's look at 1. Alright, so there are the pins for that. We're just going to look at 0 to 1 as far as the values go, just because your scaling of the output of the PWM is going to depend on what you're running with it and how you want it to work. So we're just going to play around with just making it output 0 to 10 volts based on 0 to 1 in LinuxCNC. We could scale it so that it was 0 to 10, but really you'll understand that you can set the scaling of the pulse width modulated module however you want it. So anyway, so let's how do we want to do this? Well, I know pin 1 of the printer port is the analog, the pulse width modulated input to the digital to analog converter. So I'm actually going to move this so it's not running from the charge pump, but running to pin 1. Let me see here. Oh, I just hit the... it didn't move it much. Is this pin 1? Watch out for my big head. Where is pin 1? There it is. It's way over here. My old people eyes has a hard time reading. Alright. So, that should be the PWM gen. Now, I'm not 100% sure what it is wanting for PWM. I've read different places on the internet. It's 100 hertz or it's 200 hertz. I'm going to play around with 200 hertz. So I'm going to set the PWM gen frequency to 200 hertz for the second module. So set PWM freak. Oh, sorry. Let's do it. Whoops. We're going to set that to 200 hertz. So for this, I'm just going to enable it manually. So I'm going to set PWM Gen 1 enable true. But you would probably set it to set it so that when you powered on the axis, then it would enable the PWM gen. So, you know, but let's just see what we can do here. Let's show the pins again. So we've got it set to 200 hertz. Now let's net analog. We're going to call the pin analog PWM. We're going to net PWM gen 1 PWM to parallel port 01 out. Alright. So if we set this to, we set the value to 0.5, we should get around 5 volts if everything's working right. So set PWM gen 1 value 0.5. Alright, we get 4.25 volts, you can see up here. So, not surprising. And you can see here we have pulse width modulated signal there. So that's kind of cool. So let's do 0.6. Well, that doesn't make any sense. 0.7? Yeah. So anybody want to guess what's going on here? I'll give you a hint. Let's set the parallel port 0.01. Oops. And 01 invert true. I'm going to invert the parallel port pin so it's the opposite of what it's sending. And there we go. So now you see 0.7 is 0.6, 3.8 is 0.75, 0.9 is 8.84. So not a perfect scale, and I've played around with this a little bit. It doesn't seem to matter what frequency is run to it, it's off by a little bit. So like if we set the frequency to 100, it doesn't really change the output much. I'm going to go back to 1000. It's a little closer, but if we change it to 0.5, you know, we're still off. So I'm going to go back to 200, because the thing with PWM levels, the lower the frequency, it's actually the number of levels is the base frequency, the base thread frequency divided by the PWM frequency. So I think this is 20 kilohertz. So that's at 200 hertz, it's 100 levels, which should be more than enough for this type of output for like running a VFD or something like that. And if you close the loop, it's even better, because then, you know, this works out to a better... The scaling doesn't matter as much, although the closer you get it, the better it is to tune, or the easier it is to tune. But, yeah, that's the kids upstairs. So how would you linearize this? Well, let me goof around with this, because right now, if I go 0.2, we get 1.4. So what I did the last time I played with this, and this is all wrinkled, is I actually figured out if 0.1, if I want it to be 0.1, I need to send it 0.146. So the easiest way to do this is to use the line curve component. So let's look up line curve, lin curve I should say. Alright, so it's a one-dimensional lookup table that smooths between the points. So let's play around with this. I'm going to let's see, I don't remember how I did this. Give me a second. So if we do load RT line curve, line, personality, I think, is equals, and we want 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think that's right. Does increase not required. Components can be a two-dimensional graph. Maximum resistance is 16. Okay, so personality is the number of elements. So there we go. Now I'm going to add the function to the servo thread. Show pin line curve. Oh, and then there's parameters. There's in out. Oops. Alright, so there's the X and Y for those. So I'm going to do line set P. 1 is 0.1. And I'm just going to go through these. 2 is 0.2, 3 is 0.3, whoops, 0.3, 4 is 0.4, 5 is 0.5, 6 is 0.6, 7 is 0.7, and 8 is 0.8, oops, 0.8, and 9 is 0.9. Alright, and actually, and is 1. Alright, so now if we look at those again, we have the input set, and now we need to set the output. So 0 is 0, so we're going to set 5 value (01) is 0.146. Alright. And 2 is 0.267. 3 is 0.378. 4 is 0.481. 5 is 0.579. 6 is 0.671. Oops. And 7. Now these would all be put in the HAL file. 5, 8. 8 is what did I just do there? .84 and 9 is 0.916 and 10 is 1. So now if we look at those parameters, we have them all set. So the question is this going to work? So what we want, we're going to show the pins. So we want the output of this to go to the input of the PWM gen. So we're going to net line to line curve out to PWM 1 value. Alright, so now if we say set P line curve in is 0.5, hey, look at that, it's 0.5-ish. I mean, it's as good as the 10-point correction that I made. 0.6 is 0.6, 0.7 is 0.7, 0.8 is 0.8, 0.9 is, it's a little off. 0.3 is 0.3, 0.2 is 0.2, 0.1 is 0.1. So if we go 0.15, should be relatively close. It isn't going to be perfect unless you pick a lot more points. But this kind of shows you how flexible LinuxCNC is. So now we could hook that to the spindle out or scale it the way we want it. Whatever. If we were doing a totally open loop control of something, we'd want that analog output to be scaled pretty closely. Let's go back to 0.5. But there you go. And this is running the printer port. Not dead yet! That's the printer port saying that. So, I don't know, it's kind of cool. So you can see the PWM signal changes as I change the PWM signal in LinuxCNC. So that's one extreme, and this is the other extreme. So I think it's kind of cool. You look at it better there. So, do we want to do something even neater? Huh, do ya? We can do one more thing here before I call it a day. I am going to use the other probe to look at the output of the PWM gen. So, and our scale, let's change the scale of, I am not very, let's do 2 volts. Oops. 2 volts. So 2, 4, 5. So, okay. Alright, so if you see me, I'll change this to 0.1. There's 0.1 volts. 0.9 volts. Alright, so let's do something fancy. We're gonna load RT SIGGEN. Is that what it's called? Oh, no space. And we're gonna add function SIGGEN to servo thread. Show pin, oops, and SIGGEN. So the frequency is already, this is a signal generator. So what it's doing is it's outputting either a sine, cosine, sawtooth. So if we net, let's do sine, well, let's call it sine wave to SIGGEN sine to PW, we're going to put it into the line curve in. Alright. Alright. So, if you look at that, it's making a sine wave, although it doesn't look quite right, and the reason is that the PWM gen outputs a plus or minus sine wave. So let's I don't know if it goes plus or minus the, yeah, okay, so we want it to be, because we want it to go from 0 to 1, so we want the amplitude to be 0.5. And we want the offset to be 0.5. Alright, so as you can see, it is drawing a nice sine wave out of the analog output based on the pulse width modulated input. Now, I've figured out a few things that I need to go over. Let's increase the frequency to 10 hertz. You can see 10 hertz is starting to attenuate. So the frequency response of this is pretty low. If we put it back to 1 hertz, we don't have any attenuation. So 2 hertz, you see we have attenuation. So, and we can do one more thing here, is I can show you what it looks like in LinuxCNC, because there's a cool thing called Halscope. We're going to do base thread, and we're going to look at signal. This should be, and then the output of the sine wave. So if we roll this and we can't zoom out anymore. That's what sucks about this. So on LinuxCNC, I can, you can see this is the sine wave. I can't actually make the trace as narrow as I can on the oscilloscope. But if we increase the frequency, you can see the amplitude is from 0 to 1. If I increase the amplitude, or if I increase the frequency to 10 hertz, you can see here there is no degradation of the sine wave. There's no attenuation compared to the oscilloscope. The thing is that the analog to or digital to analog converter is probably pretty slow in this. So the frequency response is, you know, worse than 1 hertz. LinuxCNC is outputting a perfect sine wave, well, perfect, while the output of the actual analog out is pretty slow. It's probably just a low pass filter. So if I speed or slow this back down again to 1 hertz, whoops, you can see we get a sine wave back. So you're not going to have anything better than about, and you can already see it's shifted here. You know, these should line up, the peaks and valleys should line up with these areas in the PWM signal, which it's not. So just something to think about when you're not going to be able to run a servo with it, of course, but slow reacting stuff will work just fine. So I think that's all I have for you right now, but this is kind of like a real world digital turning into analog. I thought it was kind of cool. Anyway, I think I'll sign off right there.